Hey, my name is Harsh and I'll be explaining you the circuit. This circuit is a half-adder circuit which is used to add two single-bit binary numbers. The two inputs are labeled A and B. A half-adder has two components, an XOR gate and an AND gate. So the XOR gate produces the sum output and gives output 1 only when the inputs are different. The AND gate produces the carry labeled here as carry and gives output 1 only when both inputs are 1. Now let's look at the test cases for which A is 0, B is 0. In that case, the sum and carry is 0, 0, since 0 plus 0 is 0. So when A is 0 and B is 1, so sum is 1 and carry is 0, which is true since 0 and 1 is 1. Same goes for A 1 and B 0. And when both of them are 1, then sum through the XOR gate is 1 and sum through the XOR gate is 0 and carry is 1, which actually it represents 2 in binary. So let's see the waveform. So we have A, B, carry, and sum. When A and B is 0, carry and sum is 0. When B is 1, A is 0, then sum is 1. When A is 1 and B is 0, then sum is 1 again. When both of them are 1 and 1, then carry is 1 and sum is 0, which represents 2, as I said earlier. Second circuit is an incremental circuit. So we are using 4 half adders, which we made previously. We have two inputs, A and increment, and we have two outputs, carry and Y. So we are using two splitter merger, and we have 4-bit numbers for A and 1-bit number for increment. So let's see how this works using a test case, which is let's start a simulation. When 0, all is 0, then it's 0, obviously. Let's make it 1. Since 0, 0, 0, 1 represents 1 in binary, so we get 1 here. This goes through our last half adder. This A and B input, one is 1, other is 0. 1 and 0 gives us 1. That goes through sum, which gives us 1. So 0, 0, 0, 1 is 1. Let's increment 1. So this increment comes here, 1 and 1 gives us 0 and 1. This 1 carry goes as input for the other half adder. So a 0 base 1, which gives us some 1, which gets here 1, 0, 0, 1, 0, which in binary means 2. So we get our output 2. Let's take another case. Let's take 7. 7, 1 increment, we get 8, and let's see how we got this. So here you can see it's 0, 1, 1, 1, which represents 7 in binary. So this 0, 1, 1, 1. This one comes here, A. This B increment comes here, 1 and 1 gives us 0 and 1. 0 gets here, 1 goes to the other one, 1 and 1 comes here, gives us 0 and 1, 0 goes here, 1 goes to the other carry. Again, same, 0 goes here, 1 goes to the other carry. Now 0 and 1 gives us 1 and 0. 1 goes here and 0 goes to the carry. In this case, it shows that it's 1, 0, 0, 0, which is 8. So the logic of this wave is simple. The increment is kept 1, A is 0, increment 1 gives us 1, 1 plus 1 for the increment gives us 2. This is all the way up to E, that gives us F. Then if we have an overflow, then we just give 1 to the carry, which shows an overflow. So that's for the circuit. Let's move on to the other circuit. So moving on to our next circuit. Which is a full adder. So in the circuit, we are using a 3 input XOR gate, 3 AND gate, 1 OR gate. We have A, B, and C in that is carry in as input, and sum and C out, which is carry out as outputs. So this XOR circuit and 3 AND. So we already saw how an XOR circuit works. So this does the same thing basically, which gets us the result. What is new to us is these 3 AND gates. So what we want to see is how they're connected. So each of them are connected to 2 different inputs, which shows us that in any case we can get a 1 if any of these is 1, which gives us a carry out. So let's see this as in a simulation. So when these 3 are 0, we get 0 and 0. This is just so you know, these 3 are 1 input, these are also 1 input. So you're already. So let's see for if A is 1, XOR gate since 1, which goes to sum, which is 1, this goes 0 to this AND gate, 0 1 gives us 0, so sum is 1, which gives us 1. Let's go carry in another. So when we get carry in, so what we can see is the XOR gates behave differently since we have 2, 1, and 1, 0. which is 0. But this 1 goes to the language. This is 0, this is 1. Since A is 1 and carry n is also 1, this AND is 1, which goes to an OR gate, which gives us 1. So we have 0 and 1, which represents 2 and binary. If third case, if all three are 1. So this triggers the whole circuit C. So the XOR circuit works fine. The inputs, same inputs, you get 1. All the AND gates have 1, 1, 1, 1, 1, passes 1, which goes to the OR gate, gives us 1. So 1, 1. So as you can see, we have 1, 1, 1, which is 3 binary. So as you can see, we have 1, 1, and 1, which is 3 and binary. So we get 1. So as you can see, we have 1, 1, and 1. 1, 1 is 2, and 2 plus 1 is 3. The output is 1 and 1. So 1, 1 in binary means 3. So now let's see the waveform diagram for this. As you can see, when A and B is 0, 0, everything was 0 as we saw here. A and B 0, 0, C and 1, we get some 1. A 0, B 1, then we get some 1 again. This keeps on going like this until the last, I guess, which is A is 1, B is 1, C n is 1, which represents 3. Then carry out is 1, sum is 1, which represents 3 in binary, since 1, 1 is 3. That's it for this case. Let's now move on to our last fourth circuit, which is going to be a 4-bit adder. So this is a 4-bit adder. So we are using this to add 4-bit numbers. A and B, we have a carry n, and as output we have carry out, overflow, and y. So overflow is the same that we discussed, in which in the case we had 3, 1, 1, 1, and the output was 1 and 1. So that was overflow. So in this case, overflow represents when we are out of integers. Since it represents 0 and 7 binary numbers, we can only represent these, and when we have to represent over those, then we get an overflow like we have in the case we have in front of us, which is A is 6 and B is 7. So let's first see how this circuit works. It's pretty similar to the circuits we've used before. We have splitter, mergers, and we have XOR for 4-bit adders with A, B, and carry in as input, sum and carry out as output. So we first let's take it 0 and this to 0. When all are 0, we have everything 0. Let's make it 1. This one. So 0, 0, 0, 1, we get 1. A sum, we get 1. 0, 0, 0, 1, we get 1. Let's make it 2. In this case, it should be 3, right? Since 1 and I think it malfunctioned. Okay, so since 1 and 2 is 3. So let's see how this works. So 0, 0, 0, 1 is 1. We get this 1 from here. This goes in A sum. This goes here 0. And we have this 2. So 0, 0, 1, 0 is 2 in binary. So this 0 comes here. This goes to B out, B carry out. This, since A, B, C 0, 1, 0, we get sum as 1. Since one of the inputs from A and B is 1. Sum is 1, we get 1, 0, 0, 1, 1, which is 3. Since 1 and 1 in binary is 3. Let's see as let's add one carry in. Okay. So this is the carry in which we got. Okay. Let's carry in. This goes here. A is in this case A is 1, B is 0, carry in is again 1, which is actually 2, which goes 0 and 1. So 0 goes from 0 goes from C sum here, and 1 goes to carry into the next. So what we see here is that every output, every input for A is from this one, the first one, which goes to A sum. I mean, which goes to A. These every B are connected to B, and the carry ends are just the number which we added. All right. So these are coming from these numbers. So we get this. So what we should see is these all A are going to the inputs of the full adders. These B are going to the inputs of the B of the full adder as well. We get this carry in, which is going to this, and then it is being carried out to another carry in, and same all the way up until here. We have an XOR gate which is connected here, and it actually shows us the overflow, since 0, 0 is 0, and for XOR gate to have overflow, we have to have 1 as 1, which represents an overflow situation. Now let's focus. Let's see overflow situation, which is 6 and let's take any number bigger than let's go with 7. So 6 and 7. So 6 goes from here, which is 0, 1, 1, 0. So it goes from here, it comes to a sum. We get this one from here as well. These both are 1, 1, which gives us carry out and sum as well, since Cn is also 1. So 3 is 1, 1, and 1 goes here, 1 goes here for the carry in, and this carry in, it gets shit. So let's see this as inputs. So 6 and 7. These 6 and 7, well, these goes through these gates. So let's just see from the last one. So we get one here. We got one from this 0, 1, 1, which goes 0 and 1, which represents 2. So this one comes here. So we get A and B, which, as I've already told, they come from different ones. So A and B, both are 1. Carry n is 1, which gives us 1, 1. So the 1 goes here. This 1 goes to the carry n of the other full adder. Same happens again. A comes from this, B comes from this. Both are 1, 1. Carry in is again 1, which gives us 1, 1, goes 1. Same happens again, which gives not same, but quite similar. This is 1, these are 0, 0, which gives us only a sum as 1. Only sum as 1. Sorry, I've had this habit of reading it as a sum. A is 0, B is 0, C is 1, which gives us sum as 1. So this is 1, 1, 1, 0, which in binary means E. So this is how we get E. And what we have to focus here is this certain situation. In this certain situation, we got an overflow. And how we got this? So since numbers are limited here, like we only have 0 to 7. So it's to represent numbers, we have to have overflows. So now let's focus why there is an overflow. So as we can see, we have 6 and 7, which leads to 13, which is E. But now we have unsigned bits and signed bits. So when unsigned bits are used, then it's 13. But we don't know when we use signed bits, when we have the 2's complement. In that situation, we can have an overflow. So right now our circuit is detecting a signed overflow, not an unsigned overflow, which logically means that overflows actually occurs in signed additions when the result is outside the representable range, which is 0 and 7. So it's -8 to 7 for the signed numbers, and for the unsigned, it's 0 to 8. So that's why we had an overflow. Now let's see the waveform diagram for this. This is same 0, 0 gets us 0, 1, 1 gives us 2, 2, 2 gives us 4, 3, 3, 6, 1, 1, 2, 2, 2, 4, 3, 3, 6. It's pretty much same all the way till the end. That's it. Thank you for watching, and